Thank you all for joining me for my dissertation defense, and hello to everyone on Zoom as well. And today I'm going to talk about prediction and planning for safe perturbation recovery during motion. So my dissertation is motivated by preventing older adult falls. 1 in every 5 falls in older adults causes a serious injury, such as a head injury or a broken bone. And every year, the cost of these fall-related injuries is about $50 billion in the US, the majority of which is shouldered by Medicare and Medicaid. And falls and fall-related deaths in older adults increase each year. And falls among people with lower limb amputation are understudied, but it is estimated that lower limb amputees of all ages fall at similar rates to able-bodied people over 85. And older amputees are at greater risk of fall-related injury than their able-bodied counterparts. And even if no injury occurs during falling, which is often the case for younger people with lower limb amputation, falls can still cause decreased balance, confidence, and social participation. And so my dissertation focuses on preventing falls in older adults and people with lower limb amputation. One way to identify falls is to identify those who are most at risk of falling and then provide targeted physical therapy. And in this case, clinicians often look at the sit to stand motion because it requires high torques and precise balance control. And some questions we might have while studying this motion are, will this person become unstable while they're standing up? And how will this person respond to unexpected disturbances? Another way to prevent falls is to use wearable lower limb robots, such as exoskeletons, or lower limb robotic prostheses, in the case of the person having a lower limb amputation, to assist with stumble recovery. And in this case, we have questions such as, how will this person respond to unexpected trips during walking? And how can we plan robotic prosthesis behavior in order to react to the trips? And lastly, for all fall prevention methods, we're also interested in making sure we can address those barriers for clinical and real-world adoption. So my dissertation contributes to both of these approaches in the following 5 chapters. First, quantifying dynamic stability during sit to stand, using inverse optimal control to understand more about perturbation response during sit to stand, predicting human responses to trips during walking, planning trip recovery behavior in lower limb robotic prostheses, and lastly, a technology assessment for robotic lower limb prostheses. And my contributions to each of these areas are listed here, including journal papers, conference abstracts and presentations, and 2 open source data sets shown at the bottom. So due to time constraints, I'll only be talking about 4 of the 5 chapters today, and we'll use this slide as an outline throughout the presentation. And let's jump in to the first chapter. So currently, clinicians diagnose fall risk using motor assessments such as the timed up and go or the Berg balance scale. Another method is to use questionnaires that ask people about physical activity or fear of falling. But none of these methods have been shown to reliably predict who will fall. So in this study shown here, researchers evaluated a bunch of different fall risk measures, normalized and averaged the scores, and found no significant difference between those who ended up falling and those who didn't. Model-based methods can offer an advantage by quantifying stability constraints. And often when we're looking at models of human motion, a place to start is a pendulum model shown here, where the base of support represents the person's feet, and the center of mass is usually located around the torso. And when a person is standing still, the condition to avoid falls is rather simple. We want that center of mass to stay within those base of support bounds. But when we get into dynamic motions, such as sit to stand, we have some more constraints because velocity must also be accounted for. So here, for example, the center of mass is outside of those base of support limits, but the person has a forwards velocity. And depending on the magnitude of that velocity, they could still be able to avoid falling. And researchers have also shown that acceleration is important in measuring dynamic stability. And so drawing from this, a research group proposed the region of stability for the sit to stand motion. So this green region shown here represents the set of center of mass positions and accelerations at seat-off during the sit-to-stand motion that lead to successful standing. But this region shown here might not accurately quantify an individual's stability because it only looks at one point in time, and it's also not specific to an individual. But in reality, there are a number of different ways that people can stand up from a chair, ranging from quasi-static on one end. This is where the center of mass remains within those base of support bounds throughout the motion, to momentum transfer on the other end, where the center of mass is sort of thrown forwards using our momentum. And a person's natural sit-to-stand strategy lies somewhere along this continuum. And so we're interested in developing a stability metric for sit-to-stand that depends on an individual's chosen control strategy and varies throughout the sit-to-stand motion. And to do that, we'll use reachability analysis. So to get an idea for reachability analysis, let's take a look at an initial condition of a dynamic model shown here, x0. And if we have some system dynamics and control law, we can integrate this point forward in time to obtain a trajectory. If instead we have an initial set, the forwards reachable set represents the set of states the model can reach under the same dynamics and control law. And if instead we look at a final set, then the backwards reachable set represents the set of states that can arrive at that final set under the same dynamics and control law. So for sit-to-stand, we can think of this final set here as successful standing. And then the backwards reachable set represents the set of all states that can reach standing under the model's dynamics and control law. So let's go into this in a little more detail. Here we have an individual's nominal sit-to-stand motion, and we can build a model of this motion. And for this cartoon, I'll lump all the states together on the y-axis and plot them through time. So under this nominal control strategy, there are certain perturbations like this forward force shown here that the individual can successfully recover from and still reach standing. But if that forward perturbation is too strong, the individual might be forced to switch their control strategy and take a step forwards in order to avoid falling. And if the perturbation is applied backwards, the individual might have to sit back down. So we're looking for an object that will be able to predict that someone will have to switch their control strategy, take a step or sit back down in order to avoid falling during sit-to-stand. And we call this object the stability basin, and it looks like this gray region shown here. So when trajectories exit the stability basin, we predict that an individual will have to change their control strategy, again by sitting or stepping, in order to recover. And previous research has found that stability basins can better distinguish between more and less stable control strategies than the region of stability that I presented earlier. In this chapter, we show that it can accurately predict that a person will become unstable. And so to do this, we conducted a perturbative sit-to-stand experiment with 11 able-bodied subjects. And in this experiment, we introduced these forwards and backwards forces using motor-driven cables applied to the subject's center of mass. So these cables could pull the subject either forwards or backwards as they were standing up from the chair. And we define a successful trial as those where a subject was able to stand up without moving their feet, and then sitting back down and stepping forward were both deemed as failed trials. So now I'll walk through our pipeline for computing the stability basin. So here we have, again, an individual's sit-to-stand motion, and that black dot represents their center of mass throughout the motion. So we can use that center of mass to build a telescoping inverted pendulum model, which has 4 states, the horizontal and vertical positions and velocities of the center of mass. The model also has 2 inputs, a horizontal and vertical forces applied to the center of mass. Next, we want to develop a model for the control strategy that the individual is using during sit-to-stand. And so we found that fitting a single controller to these data was difficult. And so instead, we solve for lower and upper bounds at each point in time based on the observed successful inputs. So now let's look at some successful sit-to-stand trajectories. So recall that our model has 4 states, so we can't plot them all together. So here I've broken it into horizontal and vertical projection on the left and right. And we're interested in using these trajectories to create a standing set, which is a shape that encompasses all of the observed final successful states. So these gray boxes here represent what it means for our model to successfully reach standing. But representing sets, such as our standing set, is often computationally taxing. And so we use an object called zonotopes in order to represent sets efficiently. So let's say we're interested in representing this gray set shown here. A zonotope represents it using a center and 2 generators, G1 and G2. And with that, the zonotope uses 3 vectors to represent the entire set of states shown in gray. So here's an example of our zonotope representation of the standing set. All of those dots are the observed final successful states from one subject's sit-to-stand trials. And we essentially use a zonotope to draw a box around it. We use an open source toolbox called Cora to compute the standing set. And we also use Cora to compute the stability basins. So Cora uses the standing set, the model of the individual's sit-to-stand, and the model of their control strategy to over-approximate the backwards reachable set. So this gray region shown here are the set of all states that can reach standing under the model's dynamics and control strategy. And next, we want to validate that these stability basins can accurately characterize when trials will be successful or unsuccessful. And so here we see that all of the blue successful trials are contained inside the stability basin, so they're accurately characterized as successful. We also want to check that trajectories exit the stability basin before that change in control strategy occurs. So in this instance, the subject was pulled forwards during sit-to-stand and had to take a step in order to avoid falling. And so we see that the trajectory exits the basin, where we see that triangle, and then the step is initiated after the trajectory leaves the basin. Likewise, in this case, the subject was pulled backwards and had to sit back down. And we see that the trajectory once again exits the basin at the triangle before that sit was initiated at the plus sign. So we conduct this validation process across all subjects and trials. And we first check that successful trials remain inside the stability basin. And then we predict steps before the subject begins to lift their foot and sits before center of mass velocities become negative. And as we can see here, we're over 90% accurate across all subjects and trials here in characterizing a stable region between those successful trials and the failed trials where a step or sit occurred. So in summary, stability basins use an individualized dynamic model and control strategy and quantify the model states that can successfully reach standing or predict when failures will occur. And so stability basins show promise for identifying those most likely to fall by accurately characterizing our stable region during sit-to-stand. But also these predictions could inform wearable robot controllers. For example, if we know that a control strategy will switch, a exoskeleton controller, for example, could adjust its own control strategy in order to accommodate that. And with that, I'll move on to the next chapter, predicting swing hip responses to trips. So many people with lower limb amputation use passive prostheses. And these prostheses have mechanical components, such as a spring or a damper, to provide assistance during movement. Robotic prostheses have some sort of actuation, like a motor, that can supply active power to joints. And using this actuation, robotic prostheses aim to more closely mimic able-bodied motion. So here we have in the dashed line an able-bodied reference trajectory. compared to a robotic prosthesis behavior in blue. And by doing so, increasing overcompensation on intact joints and limbs during walking and the associated pain that comes with it, as well as decreased energy cost. However, if an unexpected trip occurs during walking, these robotic prostheses can also pose a safety risk because they can supply very powerful torques. And so in order to ensure safety during trip recovery, we need accurate predictions of how the human will respond to a trip. And in this chapter, I focus on predicting variables of the swing hip, particularly the hip angle, hip height, and the hip anterior posterior position, which just means forwards and backwards position. We also need to generate these predictions quickly because studies have shown that when tripped, the human reflex response time is on the order of 30 milliseconds. And so if we want the robot to be able to react to the trip with the human, we want to generate these predictions before the human starts reacting. So to generate these predictive trip recovery models, we ran a trip recovery experiment using tethers attached to subjects' feet. And we applied brakes to the tethers during certain points of the swing phase in order to temporarily stop the forward motion of the foot. So as if the subject was running into an obstacle. And we used various sensors to collect data during this experiment, such as motion capture, force plates on the treadmill, and load cells measuring tether force. So in this experiment, we collected data from 16 able-bodied subjects. And we wrote a custom targeting algorithm to randomize these trips between leg side, percent swing phase, time into each 20-second trial, and the duration of the brake applied to the tether. And in this work, I'll report results for 957 trips total across all 16 subjects. So now I'll show a little highlight reel of 5 trips. You know, this is what we're all here for. I'll play each one in slow motion after. All right, and as you may have noticed during looking at those 5 trips, humans use different types of strategies to recover from these trips. So one is elevating, where the foot elevates over the obstacle with the heel striking the ground in front of the body. The next is delay lowering, where the foot initially elevates and then contacts the ground behind the body with the toe striking the ground first. And the last is lowering, where the foot is immediately lowered behind the body, again with the toe striking the ground first. And we observed these same trip recovery strategies in our subjects in this experiment. So here we're plotting heel height versus percent swing phase. And the thick black line indicates average nominal heel behavior for untripped walking. And we've sorted them into the 3 strategies here. And as you can see, even within a given trip recovery strategy, there's lots of kinematic variation in how this one subject recovered from trips. And since we're interested in the associated swing hip motion, we also see kinematic variation there. In particular, we're looking at the hip angle. Again, this is sorted into 3 strategies, and we have the thick black line indicating nominal behavior, the hip height, and the hip anterior posterior motion, which most closely resembles nominal behavior during trips. And so we fit Gaussian process regression models to these data. Which has been shown to successfully estimate hip recovery behavior in other perturbative experiments. The input to our model is the swing phase value, so from 0 to 100% swing phase. And the output is those 3 hip response variables of interest: angle, height, and AP position. And a different research group has already developed an algorithm to predict which strategy someone will use after a trip. And so in this work, we fit separate models for elevating data, delay lowering, and lowering. And we train these Gaussian process models offline, which generates a mean prediction for each response variable, shown here in green. And then after a trip occurs, we condition that prediction online on pre-trip points. So again, we have our mean prediction shown here, which is computed offline. And it has associated covariance, which is not plotted. And then when a trip occurs, we can measure the pre-trip points for this particular trial, shown in the black dots, divide our mean and covariance into these completed and future portions, and then use that to generate a conditional distribution with the mean plotted here in pink. So walking through this entire process again, we have, again, this mean prediction computed offline, the pre-trip points, generate a conditional prediction and confidence interval, and then we can compare that to the subject's actual trajectory to see, does it remain inside those confidence bounds, and what's the prediction accuracy there. So in our paper that's shown at the bottom of this page, we compared the GPR models to a time series neural network and a dynamic pendulum model. And we found that the GPR models exhibit the highest prediction accuracy in the lowest computation time, with a mean prediction time of 2.7 milliseconds, much under that sort of 30 millisecond goal we have for human reflex responses. So these model results show promise for prosthesis use by generating accurate and quick predictions. Of course, we developed this prediction model for able-bodied data from our trip experiment. Subjects with lower limb amputation have exhibited the same types of trip recovery strategies as we observed in our own experiment. However, future work will have to investigate the same model's prediction accuracy for this data of people with lower limb amputation tripping. And we also only looked here at relative accuracy between three types of models. But one other question we might have is, what's the absolute error we want to allow in any sort of robot control model? So developing ways to sort of gauge how much error we can allow when we're developing controllers for trip recovery. And with that, we'll move on to planning trip recovery behavior in lower limb prostheses. So robotic prostheses typically have three levels of control. At the high level, the prosthesis asks, what task does the human want to accomplish? And this could be walking upstairs, or walking on level ground, or sit a stand, etc. At the mid-level, the prosthesis has to know what reference trajectories are needed to actually accomplish that task. And so here, for example, are typical knee and ankle angles throughout the swing phase that are used for level ground walking on a prosthetic knee ankle. And as we can see, for different tasks, these reference trajectories are different. So for stair ascent, we see a completely different shape of knee and ankle angle. And normally these trajectories are found by collecting data from able-bodied subjects accomplishing these tasks and averaging them across subjects. Now at the low level, the prosthesis has to actually produce the reference trajectory motion by setting the correct current to the motors. When a trip occurs during walking, mid-level control is especially difficult because we don't have that sort of average behavior we have for stair ascent or level ground walking. And that's because trips can occur at any point in the swing phase. And as we saw in the previous chapter, there's a large variation in human trip responses. And incorrect torque magnitude or timing when a human is trying to recover from a trip could end up causing an additional disturbance to the motion. So given these challenges, it seems like online optimization could help generate these reference trajectories after a trip. So if we know the current human prosthesis configuration right as a trip occurs, we could use optimization to generate those knee and ankle reference trajectories that give the human the best chance at successful trip recovery. And so optimization problems have constraints which can help us enforce safety, i.e. by saying, don't scuff the toe on the ground as we're trying to recover from this trip. But the optimization problems also must have low computation time. Again, the entire swing phase of motion is usually around a half a second. And reflex responses to trips, as I said earlier, is around 30 milliseconds. So one other research group has generated an optimization planning framework for a different type of perturbation. And in this case, they examined hip drop perturbations when the hip suddenly lowers during the swing phase. And so in this framework, they first predict what the swing hip will do, similar to what I did in the last chapter. They use that hip prediction to define a set of unsafe knee and ankle angles, shown in the red here, which would lead the system to have a toe scuff during this hip drop. And then they solve for optimal reference trajectories online that avoid those unsafe regions. But there are some challenges related to this work if we want to apply it to trip recovery. So first, the authors only use the most likely estimate of human trip response. But if we want to increase safety, we like to plan trip recovery behavior for a set of predicted human behavior, i.e. the reachable set, as I introduced in the first chapter. But doing real-time optimization with sets of predicted human motion is computationally challenging. The other method also assumes that touchdown time and the desired final prosthesis configuration are known at the end of the step. However, if we have uncertainty in our predicted human response, we now don't actually know when touchdown time will occur. And we want to make sure that whenever it does, we're satisfying constraints for a successful recovery. So our proposed framework plans trip recovery trajectories online that account for sets of predicted human behavior and incorporate uncertain touchdown time and configuration. Once again, we're going to use our able-bodied trip data set in this chapter, but because we're investigating prosthesis motion, we leave the hip movement as is and we analyze real human trip recovery behavior. And then we replace the knee and ankle with a prosthesis in simulation. So we use a kinematic model in this framework with a human and prosthesis subsystem. And the model has 5 states: the hip height and the hip anterior posterior position, and then the hip, knee, and ankle angle. So now I'll walk through the pipeline for this planning framework. And the first step is to generate those reachable sets of what the human swing hip will do after a trip. And shown here in these stick figures is one trip recovery response we observed in our data set. It's an elevating strategy. And so to get those predicted sets of human hip response, we can use our Gaussian process model predictions and the associated uncertainty from the previous chapter. But as with the stability basin chapter, to efficiently represent these sets, we use zonotopes. So now we have a zonotope representation of the set of hip positions throughout the swing phase to recover from this trip. But we also have uncertainty in the hip angle, which in turn causes an uncertain set of swing knee locations. So to understand how we go from sets of angles to sets of joint locations, let's quickly take a look at this link here and say we want to rotate this link by a range of possible theta values from theta 1 to theta 2. Well, that would produce a range of possible link locations after that rotation, shown here in the second gray link. And with our hip angle, we again have sort of growing uncertainty over time, which might look something like this as it's rotated. So now we can use the predicted sets of hip angles to generate a set of predicted swing knee locations for the prosthetic knee. And note that those knee zonotopes are larger than the hip zonotopes because uncertainty from the hip angle is added on to uncertainty in the hip position. And we generate these conditional prediction and zonotopes online. Next, we want to create similar reachable sets for the prosthesis heel and toe. So the heel and toe reachable sets depend on 2 things: the predicted human set and its uncertainty, and a range of possible prosthesis, knee, and ankle kinematics that we can choose during optimization. So our goal is, after trip occurs, to select one reference trajectory for the prosthesis from a range of possible behavior. And to do that, we form a parameterized range of possible prosthesis kinematics. So we form these parameterized trip recovery libraries, as we call them, by looking at observed trip recovery angles. I'm showing it for the knee here, but we also do the same for the ankle angle. So here we have a range of possible knee behavior exhibited during elevating, delayed lowering, and lowering strategies. And here we've assigned each trajectory we've observed a value k from -1 to 1. And we've also plotted the mean here in the thick black line. So we fit polynomials to the difference from the mean in order to create our trip recovery libraries. And these polynomials are a function of percent swing phase and also that k value from -1 to 1. That produces a polynomial library of possible knee recovery trajectories. And these are parameterized again by k from -1 to 1. So now we have a parameterized set of knee and ankle angles. And once again, we can take those angles and turn them into parameterized sets of joint locations, in this case, for the prosthesis heel and toe. So walking through where we're at so far, we have the swing leg configuration right at trip onset. We have predicted sets of hip and knee locations from our Gaussian process models. And then we have parameterized reachable sets of the prosthesis heel and toe, shown in orange and purple. So we form those parameterized trip recovery libraries offline, but then online we compute the heel and toe reachable sets. So we can line it up with the trip onset configuration. Now we're ready to move on to forming those costs and constraints for a successful recovery. But before we do that, I'm going to introduce one more operation we use with these reachable sets that can help us form constraints and evaluate them quickly. So let's look at one toe reachable set at one point in time. And here we have this purple shape encompasses, again, the human prediction and its uncertainty, and also a parameterized range of prosthesis behavior for k knee and k ankle in -1 to 1. But if we pick a specific k value for the knee and ankle, thereby selecting a trajectory for the knee and ankle, we get a subset of these reachable sets shown in the darker shapes. And this corresponds to specific prosthesis reference trajectories, but still encompasses that human uncertainty in trip reaction. And we call this process slicing. So then our constraint for safety is going to be to avoid toe scuffs as we're recovering from the trip. So as you can see here, those purple reachable sets have places where they intersect with the ground. And so we define k scuff as all k knee and k ankle that cause the sliced toe reachable set to intersect with the ground. And our constraint during optimization is going to be to avoid those k values. Note, again, I've been doing this all for an elevating trial, but for delayed lowering and lowering, the toe actually contacts the ground first as the foot moves behind the body. So we want to avoid heel scuffs as we're doing that toe strike for those two strategies. So for our cost function, we want the heel to be placed near a desired set anytime ground contact is possible. But a question could be, how do we define a desired set for heel strike locations? And intuitively, we think that foot placement should depend on the hip anterior posterior motion. If you imagine having a very high forwards hip velocity, you might expect that you would need to place your foot out further in front of your body in order to maintain balance during walking. So we fit sets of hip AP position, velocity, and heel strike location to the observed trip recovery data. We do this for elevating and then delayed lowering and lowering. And note again that the z-axis for the latter two strategies is toe strike because the toe contacts the ground first, in those two cases. So if we look at a cross section of this set corresponding to a particular anterior posterior hip motion, we get a 2D set of hip velocities and heel strike locations that was observed in our trip recovery data. So for a specific hip velocity, we get a range of possible heel strike locations. And we use this green interval here as a target set to define the range of desired heel strike locations corresponding to a specific hip velocity and position. So back to our cost function. We've now evaluated those heel reachable sets by picking a specific K knee and K ankle and getting those sliced reachable sets in the darker orange. And let's look at the first instance in time where the sliced reachable set intersects the ground. We can look at the corresponding hip predictions and use that to get a desired set of heel strike locations for this one time step. And since the slice here, the darker orange, lies inside the bounds of that green interval, we define the distance from the target set, dxt, to be 0 in this case. For the next time step where ground intersection is possible, we can again look at the corresponding swing hip motion and use it to map to a separate target set for this time step. And here, the green interval does not completely encompass the slice reachable set. So we have a distance outside of the target set that is non-zero in this case. So our goal is to minimize that distance outside of the target set for the endpoints where ground contact is possible. And in this case, n equals 2, because there were 2 slices where ground contact was possible. Again, we swap the cost to be on toe placement for the other 2 strategies because the toe contacts the ground first in those cases. And we generate this costing constraint online. So now that we have everything else in our framework ready, we're ready to solve the optimization problem right after the trip. And the problem is given by finding K knee and K ankle that minimizes the distance outside of the target set anytime ground contact is possible, such that K knee and K ankle are not in that set of K that causes toe scuffs. And we solve this using MATLAB's fmincon because it works well with nonlinear costing constraints like the ones we have in this problem. And in previous versions of this implementation, we've had a mean planning time of 94 milliseconds. That includes generating the reachable sets, the costing constraints, and running the optimization. That's not quite our goal of that 30 millisecond range of human reflex responses. So we still have some work to do with reducing computation time. And we're confident that all these operations are parallelizable and we can get down to that 30 millisecond range. So in summary, oh, not in summary, not ready for that yet. So now we'll evaluate the trip recovery data set using ground truth swing hip states observed in our trip recovery experiment. And then we solve the optimization problem and simulate the solution it generates for the prosthesis knee and ankle joint if the optimization generates a feasible solution. Our evaluation criteria is to check that the system avoids foot scuffs, and we compute the distance from the target set at touchdown. And in this case, the distance from the target set is 0 because the heel landed inside that bound of green shown at the bottom. We compare our method to a nominal impedance-based controller, which is a popular controller for level ground walking on robotic lower limb prostheses, and is likely what would be on the prosthesis when the trip occurs if our planner wasn't in use. And if our solution doesn't generate a feasible solution, our framework currently defaults to that nominal controller as well. So here's an example result of an elevating trial. On the left here, we have what the subject actually did to recover from this trip. Here's the solution generated by our proposed framework. We can see that we do not scuff the toe on the ground, and we do place the heel in that desired range. Impedance-based control, on the other hand, does have a toe scuff occur in this trial. in mid-swing. Here's a delayed lowering example. So here again, when we're looking at the subject's ground truth, we can see that that toe was placed on the ground first after the trip. And our framework also places a toe on the ground while avoiding heel scuffs in this case, but impedance-based control has heel scuff in this case. Lastly, a lowering trial, same thing. We also have the toe placed on the ground in this case, and we observed many heel scuffs from the impedance-based controller for these trials. So across all subjects, our proposed framework generated a feasible solution for over 87% of trials, and then avoided foot scuffs for over 99% of those trials, with a mean distance outside of the target set a touchdown of 3.4 centimeters. In comparison, the nominal impedance-based controller avoided foot scuffs for only 56% of trials and had a larger distance outside of the target set. But let's take a look at those cases where our method was unable to avoid foot scuffs. So here we have an example trip where we have a swinging leg configuration right at the trip onset and our set of predicted hip locations. Now, our optimization tries to avoid foot scuffs for that entire set of predicted behavior. And then we evaluate it again by checking what the human hip actually did in this case, and then plugging in our optimization solution for the knee and ankle angles. But we can see in this case, there's a point in time where the human hip actually exits that range of predicted hip behavior. And so in that case, our planner was only planning for the set of gray zonotopes, and the hip exited that region. And then consequently, we have a toe scuff occur right around that same time. So one solution to get this up to 100% avoid foot scuffs is to increase those confidence bounds on our hip predictions in order to have a larger reachable set that we're planning for. However, with larger reachable sets, we'll probably get more toe ground intersection and likely get some more higher infeasibility rates for our optimization problem. So we have to sort of balance those two objectives. So in summary, I've presented a proposed trip recovery framework that uses Gaussian process model predictions to generate reachable sets of the predicted human response, reachable sets for a range of prosthesis behavior, and then solves an optimization solution that avoids foot scuffs and places the heel, in this case, as close to the target set as possible. And with that, I'll move on to the last chapter, conducting a technology assessment for robotic lower limb prostheses. And the central focus of this chapter is how do we assess the societal impacts of an innovation? So here are three types of robots that some of us work on right here in the robotics building. And we as researchers might have certain goals that motivate our work for these types of robots. But as many of us, I'm sure, have had conversations about robots in everyday life, there are also plenty of concerns about each of these robots. And scholars in science and technology studies argue that we as engineers should consider the potential consequences of the technologies we develop in order to address these concerns. And this can be either through exploring new research directions as roboticists or proposing new policy to address the concerns on that end. And for those of us who work with assistive robotic devices, we have other concerns to keep in mind, such as user safety and comfort, the cost and insurance coverage of these devices, accessibility requirements for their use, such as height, weight, or fitness level requirements, clinical or real-world translation, and the standards and regulations used to approve this for commercial use. And so a technology assessment is a form of policy research that examines the short and long-term consequences of a technology. And so in the last chapter of my dissertation, I describe a number of different technology assessments that we as engineers could use to evaluate the technologies that we work on. And these could get input from experts, stakeholders, those involved in designing or using the device, or lay people who may or may not have especially an interest in this type of technology. And I also present some preliminary results for a technology assessment of robotic lower limb prostheses. And in particular, I'm interested in the standards and regulations used to evaluate these designs. So first I ask, how do prosthesis developers evaluate their designs? And often this is by comparing to observed able-bodied data. So here we have a paper where data from 3 amputees using a robotic prosthesis was compared to mean and standard deviation of a healthy data set. But a technology assessment prompts us to ask, what subjects are used to define healthy here? Are they all, for example, very young and athletic subjects? And is that the same type of motion that the person with a lower limb amputation wants on their prosthesis? So next, I asked, how do these evaluations influence regulations? And I found that these regulations are sort of co-produced with the academic evaluations. So first, researchers sort of converge on evaluation criteria in academic papers. And then the FDA draws from that in order to develop regulations to approve devices for commercial use. But in turn, that sort of enforces that researchers will continue to use the same standards in order to evaluate their designs, because generally researchers would like to commercialize their products. And so, so they'll use whatever the FDA is listing to approve them. And lastly, we can ask, how can we adjust this process to align with stakeholder concerns? And maybe as engineers, the first way we can look is to think critically about what we're using to evaluate our designs and see if they consider these possible concerns such as safety, accessibility, or clinical translation. And certainly in my own work, we use able-bodied data from young, healthy subjects. So this technology assessment prompted some self-reflection and will shape sort of the future work for all the frameworks I presented in this talk today. And lastly, if this seems interesting to any grad students, you can check out this certificate program in the School of Public Policy, which I completed during my time as a PhD student. So in summary, my dissertation aims to reduce fall risk in older adults and amputees. And in order to assess stability during sit-to-stand, we proposed stability basins to characterize a dynamic stability throughout the sit-to-stand motion. And in order to increase trip recovery safety in robotic prostheses, we developed a prediction and planning framework to safely and successfully have the human and prosthesis recover from a trip. And lastly, I presented preliminary results from a technology assessment to see if we could help increase clinical use and real-world translation of the frameworks in this dissertation. So for future work, we've shown that stability basins can accurately characterize stability during sit-to-stand. However, our next question is, can they identify who is at risk of falling? And to do this, we'd have to conduct a longitudinal study with older adults. And a study like this would involve recruiting hundreds of older adult patients and establishing a clinical partnership, and then computing these stability basins and maintaining contact with the subjects over a long period of time, say 5 years, and seeing who in this group ended up falling and who didn't, and are there differences in the relative volumes of their stability basins. For the trip recovery planning framework, we first made some assumptions that the trip was immediately detected by the prosthesis hardware, and we know which strategy the person will select to recover from the trip. Both of these assumptions are based on previous work by other researchers, but of course we would have to implement them on our own prosthesis hardware and show that they're reliably detecting the trip onset and predicting strategy selection before we continue with implementing the rest of the framework on prosthesis hardware. We also looked at swing hip predictions using data from our able-bodied trip recovery data set. And as I sort of hinted at in the technology assessment section, these kinematics here might not be the same we observe in someone who has a lower limb amputation. And furthermore, depending on what controller the the robotic prosthesis is using, that hip recovery behavior could actually change over time. And so one solution is to look at using wearable sensors such as inertial measurement units to collect data of hip recoveries while this trip recovery planning framework is in use, and continually update our predictions that way. We also form these trip recovery libraries. This is sort of the range of possible knee and ankle behavior that the prosthesis can use after a trip using this able-bodied trip data set. But again, this motion we observed here in our subjects might not be effective or comfortable for someone with a lower limb amputation during trip recovery. So in future work, we should look at different ways to form a range of possible prosthesis behavior with more input from people who will actually be using the trip recovery planner. And lastly, the planning framework I presented is very generalizable. We could look at different models, for example, 3D models that investigate sidestepping or cross-stepping after lateral perturbations, trip recovery when the prosthesis is in stance rather than swing, or even generalizing to other types of wearable robots, such as a lower limb exoskeleton rather than a prosthesis. So I'm looking forward to seeing what other directions this framework can be used for. And with that, I would like to thank my committee first. Ram is my advisor and has been a great source of support over the past 6 years. Talia has also been a close collaborator with the Stability Basin research. And I also worked on some really cool research about coral snakes with her, which I didn't present here. And then Alex Shorter and Leah Sterling have both provided wonderful feedback throughout my PhD. Alex was actually a panelist on my quals, which was about 4 years ago. So he saw the early version of the Stability Basin work. And I'd like to thank my research team, Patrick Holmes, Martine Ward, and Xinyi Liu. Especially shout out to Patrick, who has worked on every single one of the projects I presented here for the past 6 years with me. I'd like to thank my mentor in the science and technology policy research, Professor Shobhita Parthasarathi in the Ford School. And then I'd like to thank Hannah Frame and Emma Resnick for countless experiment training and troubleshooting help during my trip experiment. So thank you. And then lastly, we have to have the fun photo collage at the end. Here's Roam Lab over the course of my time here. It has certainly grown, and it's been fun to see and meet all the new members who join the lab, and to have lifelong friends from time in the lab. And also thanks to all my wonderful friends I've met here at Michigan, and for all the family visits. It's been wonderful exploring this new state with all of you, and I look forward to maintaining in touch with you for the foreseeable future. So thanks, everyone. And with that, I will take questions.